Thank you very much, Martin. That's very nice. And thank you, Andrea, as well. Thank you to both of you for inviting me. So as you said, I'm from Lyon. I work in the LAMCOS, which is the Laboratory of Mechanics and of Contacts and Structures. It's not a lab of geoscience, it's a lab of engineering, actually, of mechanical engineering. But this work I'm going to present you was done during a stay I made in Paris at the Laboratoire de Géologie at the INS with Jérôme Aubry and Alexandre Choubnel. Okay, so before going to geosciences, I would like to take a little detour about tribology, because it's one of the topics of the lab where I work. Tribology is the science of friction and wear of materials in contact. And I'm going to talk a bit about numerical tribology. So the tribology is a very large discipline with a lot of applications, but one way to unify this science is to consider that a given contact should always be seen through 3 different scales. And that's the object of the so-called Tribological Triplets, which was conceptualized about 40 years ago. And this concept says that to understand a contact, we need 3 scales. Obviously, we need the scale of the 2 bodies in contact here. We call them the first body in this framework. So that would be a cello and a bow, for example, or the 2 walls of a fault. But we also need to keep in mind, and I know that seismologists and fault mechanics scientists are very well aware of this. We always need to keep in mind that each contact takes place within a mechanical system with its own stiffness, damping, actuators, control, and so on. So that's what we call the mechanism above the contact. And there is also a smaller scale, which we call the third body. This is a scale of everything which is trapped within the contacting interface. So for geophysics, it might be called the fault gouge here. And for the cello player, it would be called the colophane, which is some kind of resin that you must put on your bow in order to get a sound. Otherwise, you won't get any sound from your cello. All right. This third body here is clearly the most complicated and the most mysterious member of the tribological triplets. We put a lot of efforts on it in tribology to understand how it gets created, how it flows, and also in our contacts, in our industrial contacts, how it gets ejected from the contact, because this is what creates what we call wear. As you see here, third bodies can have a very wide range of aspects. Sometimes it's extremely granular, like here. Sometimes it's more compacted, like here. Sometimes it flows like toothpaste, really. So it's extremely complicated to get one single description of this system. We would like to model this. So what would be the best way to model this? We can use continuous modeling. That's the first reflex of the engineer, but it's extremely challenging because there are some very complicated kinematics. We can expect a lot of mesh distortion in this layer, and we don't even know what would be the proper constitutive model for this. So there's been another approach for the last 20 years now, which is the discrete element modeling. And in this approach, we make the choice of representing this layer, this solid layer, as a collection of interacting rigid bodies like that. So the numerical technique is called discrete element modeling. It's quite widespread now in granular mechanics. And it's based on this kind of representation where each grain is a solid body with its own dynamics, and where we have interaction between these grains through contact laws which are usually based on simple laws such as friction, damping, and some contact stiffness here, although it can get much more complicated in some cases. So in this case, I showed discs because that's the historical method, but we can now extend this to arbitrary shapes of the grains and also do this in 3D if we want to. We can go further than this because classical DM, as I just showed you, deals with the interaction of rigid bodies only. And this assumption is always wrong when we look at industrial third bodies, because we have some very high contact stresses, way above 1 gigapascal, meaning that the grains don't remain rigid, they deform most of the case. They get plastified, they get sheared, and so on. So I'm going to talk a bit further in this talk about some applications where we need this. We need the grains to deform, and to represent this numerically, we need to go beyond classical DEM, and we need to discretize each grain, each body, by a number of nodes which carry the degrees of freedom in displacement. And well, I won't go too deep into the math of this, but it's a bit like a finite element method on each grain, except that we are using some shape functions which are a bit different, which are mesh-free actually within each grain. So this gives the grains a lot of robustness in the case of large deformations. And you will see that this is very useful in what's coming. So we are using this in a large number of applications. For example, in some very physical, granular physics applications, some abstract applications, where we just mix soft and rigid grains and see how this kind of mixture behaves. Depending on the proportion of soft and hard grains, you see that we have very different rheological response. Here we have only a few deformable grains within the rigid grains, and we see that they concentrate the load and they deform a lot and they feel the porosity between the grains. But in this case, for example, where we have almost only deformable grains, we see very different patterns with some localization of the stress field between the rigid grains, which act as nucleation points for shear banding in the soft grains. So this is all very complex. I'm not going to enter into the details. We also do some industrial tribology. So in this case, for example, we are focusing on the local behavior of a contact inside some parts of an aircraft engine. And we're using this method to observe what this third body implies as stress concentration patterns inside the surfaces or inside the first bodies. We see, for example, that in some cases we have the formation of agglomerates which concentrate the loads, which will eventually lead to a lot of damage in these surfaces and probably accelerated wear. So this is very interesting for the manufacturers of such systems. We've been applying this as well to the abrasive wear of diamond tools during rock cutting or during concrete cutting. And for example, you see that in this case, we're abrading some surface by some granular flow. And by zooming in, we can see that we can represent the stress concentration at the contact, the emission of acoustic waves inside the medium, and the abrasive wear with the separation of matter from the surface, and this matter then gets entrained into the granular flow. Another example of application is the wear particle creation and ejection in the tire road contacts. This has a lot of implication for public health, actually, because a large proportion of the particles in the air do not come from exhausts of cars, but from the wear of brakes and tires. So what we are trying to simulate here is the progressive ingestion of mineral grains from the road inside the degraded layer of the surface of a tire, and eventually this will lead to an evolution of the mechanical properties of this layer and probably its degradation and the emission of wear. So those were just a few examples of what is numerical tribology, and you probably noticed here and there some similarities with fault mechanics. So we are going back to fault mechanics, keeping in mind the main concepts of numerical tribology. Of course, you may feel free to interrupt me if you have some question, obviously. So back to fault mechanics. Fault mechanics is a lot about tribology. So sliding in rocks, as you know, in rock faults occurs with a wide range of seismic and aseismic events. And one usual way to understand this is to compare the weakening or hardening character of the friction load that is used or that exists in the fault with the stiffness of the surrounding medium. This is the classical view here. And instability will occur if the resistance to shear of the interface, this black curve here, decrease faster than the pulling load on the interface. In this case, you have some unbalanced force here, which means some acceleration and some dynamic slip. So if we want to investigate the stability of faults, we need basically to answer this question: does sliding make sliding easier, or is there a positive feedback or a negative feedback of sliding on itself, based on these two ingredients here, the friction load and the stiffness of the loading system? To understand this, there are a lot of different devices that are used in rock tribology. We will look at a few of them. So first one which is very useful and very common is the direct shear. It's very useful for slow slip sliding, and it allowed to document a lot of interesting data about rate dependence of faults. But only at small sliding velocities. This rate dependence is often attributed to local physical chemistry, like the aging of contacts between the different surfaces that exist within the fault. And it can be well fitted with rate and state friction laws. And it's been shown by many simulations to be relevant for slow nucleation, but it kind of collapses when we enter into dynamic sliding. To simulate dynamic sliding in the lab, the best tool is the high velocity rotary shear apparatus. You have some examples here, some classic examples. And in that case, a very strong weakening of the fault interface have been documented in a lot of experiments. They are, for example, gathered in this classical paper by Titoro and et al. in 2011. And this dynamic weakening is attributed to a wide range of possible causes. Thermal pressurization, thermal decomposition, gel lubrication, and so on. And among them, there is the melt lubrication, which is the topic that we will be talking about in a moment. Why would a fault melt? So first of all, we must remind that rock surfaces are rough at all scales. It's been known for a while, and it's been, for example, documented in this famous paper by Candlelight in 2012, where they showed that there was some kind of continuity of the of the roughness, of the statistical laws of roughness across many decades of spatial scale, I believe 9 decades, if I'm not wrong. And this is also true, for example, at the surface of any sand grain. It's been documented as well. And this has some consequences, some mechanical consequences in terms of contact mechanics. The main consequence of this is that the real contact area, that means the area where two solids really actually enter into contact, is believed to be extremely small when compared to the apparent contact area. So this picture here is extremely famous from this classical paper from Dietrich and Kilgore. And this has consequences on the location of heat creation, because this patch of contacts concentrate a lot of stress, and of course they concentrate the heat creation. And this representation is at the basis of the famous flash heating theory. This theory states that since heat creation is restricted to very small areas, we will have a very quick temperature increase in these areas, in these so-called asperities. And because of this quick temperature increase, the asperities will weaken because of local softening or melting or anything, any phenomenon which weakens the asperities under high temperature. And this would control the fold friction, because the proportion of weakened asperities will decrease the friction in the fold. And this law has been proposed by Rice in a famous paper in 2006, where actually friction is controlled by a linear mixing law between two populations of asperities, the asperities which are intact and the asperities which are weakened. And this law has been fitted experimentally several times, and usually it works pretty well. However, there is a question about this, which is how do we deal with fold gouge? Because observation and experiments show that actually fold sliding is rarely on bare rock, and most of the time it would be more appropriate to represent fold sliding as the shearing of a gouge layer and not as the sliding of two surfaces. So this is reminiscent of what I showed you about the tribological triplets a few minutes ago with this so-called third body. So observation tells us that we should account for a third body when we deal with fold sliding. So is there a dynamic weakening in a gouge layer? Since in this case, geometric asperities get much less relevant in the representation of the fold. And the answer is yes. It's been shown in several experiments. For example, in this experiment in 2010, where, so we must look here at the red curve, where they showed that there was indeed a weakening of the friction of the fold when they increased the sliding velocity. And they even had some evidence of melting, that is of glassy patches like this one in the fold gouge when they looked at it after the test. Another class of rock trigonometry apparatus is the so-called Triaxial experiments. So this one, for example, was done by Guilhem Mollon in the Laboratoire de Géologie of INSA Paris some years ago. And this kind of system is used usually to represent some laboratory earthquakes, that is, to represent some stick slip events on a very small lab size folds. In this experiment by Guilhem Mollon and with Alexandre Schubner, they were able to track the temperature increase during the sliding events. And indeed, they were able to provide evidence of extremely high temperature increases well beyond the melting temperature of the common minerals observed in rocks, like well beyond 1500 degrees Celsius. And this was confirmed indeed by observation of the surfaces after the test, where well, they could provide evidence of partial or complete melting of the gouge layer, like here, for example, or in this cross section. This is a layer of glass, so amorphous rock coming from the solidification of a metal layer, and you see that it's a few micrometers thick, surrounded by some granular gouge, which apparently didn't melt during the test. The questions I want to address today is, how does this layer appear, and what are its implications on friction, and can we simulate this numerically? So I'm going to start first with the simulation of the dry gouge, and we will introduce melt later on. But first, we need to understand what happens in the dry gouge before melting occurs. This is a sketch of the model I'm using. As you see, it's based on a granular sample, which represents some established layer of comminuted gouge. The grains are about 1 micrometer large in diameter, and the sample width is about 100 microns, and the thickness is varying, but it's a few tenths of micrometers. So we put this under 200 MPa with a sliding velocity, which is a bit larger than typical velocities during earthquakes, but I have a good reason for this. I may talk about this later on. We put periodic boundaries here on the two sides to allow sliding for sufficient distance, and we simulate this during a few tenths of microseconds. So this is supposed to represent a small patch somewhere within this interface during sliding events. If we take a closer look, we see that the shapes of the grains are chosen to be somewhat realistic. They are not circular, they are quite angular with facets. They are inspired by what we often see when we put some gouge under a microscope. And an interesting feature of this code is that it can kind of record the mechanical energy dissipation in each contact and transfer it into heat into both grains that are in contact. So we can transform the mechanical energy into thermal energy. And you will see that we make an interesting use of this later on. So typical simulations look a bit like that. So we have one fixed wall, which represents one side of the fault, and a sliding wall above, which represents the other side of the fault. And here we have a few thousand grains, which accommodate the shearing the way they want, actually. So the kinematics and the shear patterns and the motion of the grains here emerge spontaneously from the friction loads and from the shape of the grains, etc., etc. We do not control the kinematics here. So this system is extremely flexible and can tell us a lot about what happens inside the fault. We are interested in melting, so we need some heat diffusion inside the gouge. So I told you before that we are recording the heat creation inside each grain. We also can put some heat diffusion between the grain through their contacts by building some kind of thermal network here. So each grain is represented here by some kind of a circle, and each contact is represented by a segment, and you can have heat exchange between each grain, each pair of contacting grains, and all of this can also exchange heat with the surrounding medium here. so it can dissipate and diffuse energy and heat in the surrounding medium. Okay, so with this, we are able to represent, to compute what is the evolving profile of temperature within the gouge. What we see here, for example, is the thickness of the gouge from 0 to about 45 micrometers. And this is a temperature profile after 200 micrometers of slip here. And this is the other temperature profiles when we increase the slip length. So we see that temperature is steadily increasing inside the sample with a somewhat parabolic profile, and we see that after 500 micrometers of slip, we are starting to get closer to the melting point of most minerals in the fault gouge. We can also investigate the influence of the sliding velocity here. So for example, if the velocity is 0.1 meter per second, we will have, after 500 micrometers of slip, a maximum temperature close to 500 kelvins. But if this sliding velocity is 10 meters per second, the maximum temperature is much higher. It's close to 1200 Kelvin here. What this model tells us is that melting is probably going to happen in the central part of the gouge here, where the temperature is the highest, and especially in the central 5 to 10 micrometers. And this is in good agreement with what we observed in the experiments, where we had this layer of about 5-8 micrometers of molten rock. Now, how can we introduce melt inside the simulation? Because if we have this melt occurring in the central part of the layer, of the gouge layer, obviously this representation we have here will not be correct anymore, because melt will disturb the behavior of this gouge. We need to introduce melt explicitly inside the model to see how this disturbance affects friction, for example. And this is done this way by representing approximately the molten rock by a collection of highly deformable, incompressible, and viscoelastic grains. So, for example, in this case, we simulate a fully molten layer in the central part of the gouge. And as you see here, this red layer here is actually composed of highly deformable grains, which are frictionless, but which are viscoelastic in behavior. So this leads to an equivalent viscosity in this layer, which has been measured afterwards to be close to 10 Pascal seconds. And this is actually not too far from what we can find for rock viscosity, for molten rock viscosity, especially for molten silicate. So this is in the low range of molten silicate equivalent viscosity. In this case, we also record all the dissipated mechanical energy and transform into heat. The only difference is that this mechanical energy is dissipated through the viscosity of the grains and not through their frictional contacts, as was the case in the solid grains. We can pay attention at two end members. The first end member is the one with only solid grains, and we have a friction coefficient in that case, which is close to 0.5, let's say. And in the case of a fully molten central layer, we have a friction coefficient which is close to 0.1. So we have a very large decrease of the friction of the interface. But we also have very large differences in the behavior of the interface. For example, with solid grains, we have a very distributed shear in the granular layer. The full layer contributes to the velocity accommodation, while in this case, we see that all velocity accommodation occurred in the molten layer, and actually the granular layers around were not deformed at all. I won't talk about this. I will give a few elements on the volume fraction. So in the case with only solid grains, we have quite a large dilation of the grains of the sample. This is very common in granular materials. While in the case of a molten layer here, we almost have no porosity in the central part, because the grains deform so much that they close all the porosity in this part, just like if there was some liquid here. And the two granular layers around keep very dense because they were not dilated by any shear during this simulation. In terms of temperature, we see that in the completely dry sample, temperature increase is distributed in the total in the complete layer, and it's quite high. So this is after 200 microns of slip, and we already have an increase of about 500 kelvins in the central part. And in this case, it's pretty different because the temperature increase is only limited to the part which accommodated shearing, so the central molten layer. And this temperature increase is much more moderate. It's not more than, let's say, 100 or 200 kelvins in this layer. So we want to understand this. And to understand this, we are going to observe all the intermediate situations between these two end members. And for that, we are going to observe 9 simulations corresponding to increasing proportions of melt. I call this Phi-M, the proportion of melt, in the central layer. So in this case, for example, I've got 5% of melt, the red grains, here 40%, and up to 100% for the complete melting of the interface. Let's see how it behaves. So this is the case with 0% melt. So the simulation with a completely dry layer. What we see is that the full layer contributes to shearing, and that the temperature increase is distributed in all this layer, as we saw before. No, we just introduce 5% of molten grains in this central layer here, and observe how it changes the behavior. We can see that the top and bottom layers of grains here seem to be sheared a bit less. They act more like rigid or undisturbed layers, and we tend to observe that heat creation is more concentrated in the center of the layer here. With 30% of molten grains, this trend is much clearer. We see here that this granular sample is not much disturbed, this one either, and that the heat creation is much more concentrated, and it's much more intense as well here. You see that temperature increase is much more intense in this central part of the layer. With 60% of molten grains, we are getting close to the case of a suspension of grains inside a liquid. And actually, if we look at the kinematics of the grains here, that's very close to it. That's a few solid grains within a liquid layer. And we see that it concentrates all the shearing. These two parts here did not shear anything, did not get sheared at all. And when we arrive finally to the 100% of, to the case of 100% of molten grains in the central layer, we see that it's actually a very smooth sliding of, very smooth sliding of these two surfaces, and it's only sheared in the central layer. And in this case, the temperature increase is much more moderate. This will be explained by the numerical results that are coming now. First, the friction coefficients on the interface. So these are the friction coefficients that we measure during the test or during the simulations for 4 different cases with 10%, 30%, 60%, and 100% of melt in the layer. And you see that this friction coefficient clearly decreases when we increase the percentage of melt. We will focus only on this steady state part here, and we have this kind of curve. So in X here, the melt proportion, and in Y, the friction coefficient. So we go from this dry friction coefficient to this fully molten friction coefficient. And we see that this decrease is not linear, actually. It's more a sigmoid-like shape. An interesting interpretation of this is to watch the friction coefficient here, mu, as a representation of the energy dissipation inside the layer, inside the fold. And this energy dissipation comes from 2 sources. The friction between the solid grains, we call this the Coulomb term, and the viscosity of the molten grains, we call this the viscous terms. And this kind of additive energetical decomposition allows us to decompose the friction coefficient into 2 contributions. And there are the 2 contributions seen here. So for example, when we have 0% melt here, the friction is completely controlled by the Coulomb friction between the dry grains, the solid grains. And when we are at 100% molten grains, friction is completely controlled by this red point here, by the viscous contribution of the molten grains. But in between, there is kind of a mixture between these 2 energy dissipations. And actually what we see is that these contributions do not evolve linearly with the melt proportion. We see, for example, that the viscous dissipation here is larger than what could be expected from a simple mixing law between the dry and molten grains. And conversely, the Coulomb dissipation is lower than what would be expected from a linear mixing law between the dry and the molten grains. So Coulomb contribution is smaller than expected, and viscous contribution is larger than expected. And one way to explain this is that when there are some molten grains, they tend to lubricate the contact between the rigid grains here. For example, this grain here is lubricating the contacts between all the rigid grains surrounding it. And this leads to a reduction of the contribution of the Coulomb dissipation. But at the same time, if they lubricate these contacts, it means that they concentrate a lot of shearing, and that the shear rate inside the molten patches here is extremely high, which is the reason why the viscous dissipation here is larger than what would be expected solely from the proportion of molten grains. There is also what we observed a few slides before. There is also an effect on the shear profile. We see that when we increase the proportion of melt, we have a progressive localization of the velocity field, and the velocity field gets more and more narrow when we increase the proportion of molten grains. This has consequences, of course, on the shear rate. So in the case of 0% molten grains, the shear rate is distributed here and not very intense. But when we go to very large proportion of molten grains, the shear rate is extremely narrow and very high in this region here. In terms of temperature increase, this is very interesting because when we first localize the shearing, that is when we first tend to increase locally the shear rate, of course the temperature increases as well because we are narrowing the area where heat is created. But then when we keep increasing the proportion of melt, then this temperature decreases again. This is not monotonous. You see, from blue to red, we go there and we go back. And the reason is that when the proportion of molten grains gets closer to 100%, actually the friction decreases a lot, which means that the heat creation decreases a lot. So even though we create heat in much narrower section, we create heat in a much smaller amount. Okay, so here are some conclusions about these simulations. First, we saw that granular shearing localizes in a thickness of a few grains diameter, which is portray the heat projection in the center of the shear layer. And this is where melt is likely to occur first. Then we saw that the melt appearance leads to some hyperlocalization of the shearing and with a strong reduction of the friction. And this leads to a much faster, without a strong reduction of the overall friction in the first stage. And this leads to a much faster increase of temperature because we create as much heat, but in a much narrower area. And this leads to a strong weakening of the faults thanks to this decrease of the friction coefficient with the melt proportion. So we have, in this case, a positive feedback of friction on itself, of sliding on itself. Sorry. But then when the friction becomes very low, we reduce the heat production because if friction is low, energy dissipation is low and heat production is lower. And then we stabilize the weakening at that point, which means that at that point, we go back to a negative feedback of sliding on itself, which means that we will stabilize again the sliding of the fault. I will finish on a few perspectives on this work with the building blocks of a thermomechanical fault model, which would account for all this complexity in a more simplified manner. And for this, we can consider, for example, the case of a granite with 4 mineral components. And each of its components has its own melting point and also its own proportion in the mixture, in the granite. And this allows us to build a thermodynamic diagram of phases in the granite. For example, if we increase the energy density in granite, first we will obviously increase the temperature here. But then at some point we will reach the melting point of biotite. So in this case, we stop increasing the temperature, but we increase the melt proportion. So biotite melts, okay? When all biotite has melted, we increase again the temperature if we increase the energy density. And the melt proportion stays constant. Then we reach feldspar, we melt feldspar, then we reach plagioclase, etc., until we melt the quartz grains. So with this kind of diagram, for a given energy density, we can guess what is the proportion of melt and what is the temperature in the system. And this, when we combine it with heat creation and with heat diffusion and so on, can lead to this kind of system. So I'm not going to present the model which led to this because it's a very preliminary model, but we can have this kind of behavior where when we slide here, sliding distance, we first increase the temperature in the gouge, but then we reach the melting point of biotite. So we add a bit of melt in the mixture, which lowers the friction coefficient here. Okay, we keep increasing the temperature, then we reach feldspar. Feldspar melts. Okay, so we increase the proportion of melt, and when we strongly reduce the friction coefficient in the system. And by strongly reducing the friction coefficient of the system, we stabilize the temperature because we cannot produce enough energy to keep increasing this temperature. And if we represent this in the thickness of the gouge layer, so this is the position across the gouge layer and the temperature field across the sliding distance, we see that we have this progressive heating of the central layer, and it can be expressed in the melting of different minerals. So in this case, for example, up to like 140 microns, everything was dry. Then biotite melted, first in the center and then in a much wider thickness, like for about 4 micrometers. And then when we keep sliding and keep producing heat, then we melt the feldspar, and feldspar keeps melting as we keep sliding. And in the end, here we have a layer of partially molten rock here, which is about 5 micrometers thick. And if we do this with other operating conditions, we can even melt up to the quartz and have a complete melting of the interface. In that case, sorry, the friction drop is extremely strong, and we get to a friction coefficient which is closer to 0.1 here. Okay, I will end up this and just want to advertise this. I'm looking for a postdoc fellow next September in Lyon for a very nice project funded by INSA, where we will try to compare this with the results of a very novel experimental apparatus that we are building, and also extend this to a much more complex and realistic numerical model. So if you have candidates, or if you are a candidate, feel free to contact me, please. I'll be very happy to chat with you about this project. With this, I thank you for your attention, and I will take your question with pleasure. Thank you very much.